Hello everyone again. My name is Stefano Ubbiali. I am a PhD student in applied math at ETH Zurich in Switzerland. And today I'm going to present this Python library, Tasmania, which I have been developed as part of my research project. But I would like to stress that this presentation includes many contributions from people at the Swiss Computing Center, CSCS. So let's start with a bit of context by focusing on the multi-scale nature of the atmosphere. So indeed, atmospheric waves span a wide spectrum of length and time scales. As can be seen from this diagram, which I took from the dissertation of Oli Führer. And this implies that even at 1 kilometer resolution, which is kind of the standard goal for high resolution global runs, we still have some processes which cannot be properly represented over the grid as compared to processes which are fully resolved. And this is reflected in the structure of atmospheric models, which consists of two parts. We have the dynamical core, which solves the governing fluid dynamics equation over a grid. And then we have parameterization, which account for physical and chemical subgrid scale phenomena. And throughout the presentation, I'm going to refer to parameterizations and dynamical core as model components. So I will be talking about Tasmania, which is a Python library which serves three main goals. So first, it should be seen as a tool set to write model components with a common interface, which are interoperable and self-documented, and which should allow to build models with enhanced flexibility, modularity, and maintainability. And in this respect, Tasmania should be seen as an extension of an already existing framework, which is called Simple. And then we provide some utilities to write stencil applications, which are hopefully performance portable. And overall, we aim at grabbing some insights on the suitability of the Python ecosystem for the next generation of models, which will run on exascale machines. So let's dive into the components, starting with the communication. So the components talk mainly through dictionaries, where the keys denotes the names of the state variables, and the values are data arrays from the xarray package, which hold both grid values and metadata for those variables, where by metadata we mean units, dimension, coordinates mainly. And concerning the names of the variables, we propose an highly descriptive naming scheme, which consists of two parts. So the prefix of each name consists of the standard variable name, which ideally should adhere to the CF conventions, so to be descriptive by itself. And then the suffix denotes which is the location over the grid of these variables. And here I prepare some visualization to exemplify this. So for instance, when we say that a variable is defined at the U locations, it means which is staggered in the X direction, while on interface levels means that the variable sits at the lead and the floor of the cell. And we can also combine these suffixes, like at UV locations means that the variables is located at the corners in the horizontal direction. And this is turned out to be quite useful for us, because then for each component, we can specify which variables are required in input and which are the output fields which will be provided. So like kind of stating explicitly which are the terms of a contract for each component. And this not only enhances the readability of the code, but it also allows for some runtime checks, like to make sure that we are provided with all the variables that we need, that the variables are the proper units, and if not, we perform some unit conversion and transposition if needed. And then in the future, this will also accommodate some data dependencies analysis for instance, to find which is an optimal scheduling of the components. And each component retrieves the information of the grid, about the grid, from a domain instance. And domain is a class, which is actually an umbrella container, which first of all contains the physical grid over which we want to simulate the atmosphere. And because atmospheric models usually use prismatic grids, meaning that we have an horizontal tessellation, which is then extruded and cut at some vertical levels. So here when we decompose the horizontal and the vertical discretization of the atmosphere, so we have an horizontal grid object and a vertical discretization. And then, of course, because the surface is typically not flat, we also have a topography class which carry around information about the soil. And then inside domain, we have also an horizontal boundary object, which takes care of the lateral boundary condition and is in charge to produce the numerical grid, starting from the physical one. So we distinguish between these two kinds of grids because, for instance, when we work with periodic boundary condition, we typically decorate the domain with some ghost cells in order to impose periodicity in a weak manner. And so the horizontal grid of a physical and numerical grid may differ, as well as the topography, while of course the vertical discretization is not affected. And we stress here that at the moment we only support Cartesian grids or logically Cartesian grids, and support for unstructured meshes will come in the future. And now we can see some concrete example of components. So you find on the right-hand side a legend for the schematics that I'm going to show. So the first component we have is diagnostic component, which takes a dictionary state and retrieves some diagnostic quantities from this state, while a tendency component, as the name says, computes some tendencies. That means some time derivatives for the state variables. And we also have a variant of tendency component, which can also accept the time step delta t as input, for instance, for some timescale dependent computation. But we can also compose these components in a higher level abstraction, which is provided by concurrent coupling, which basically takes a state and forward it to two or multiple, actually as many as you want, tendency components, each computing some tendency, which are then sum up and provided as a single dictionary. And these components are mainly meant to implement some physical packages, while for the dynamics, we have a dedicated class, which is called Dynamical Core, which support partial time splitting, which means treating processes with different time step sizes. And to exemplify this, we can consider the line of the simulation time, where here the ticks represent increments with respect to the current time level Tn, which are multiple of the main time step delta t. And then we distinguish between slow physics processes, which occur on time scale, which are much longer than the time step delta t, and so can be updated, let's say every 4 time steps, or not every time step. A radiation is a stunning example of this kind of processes. Then we have fast dynamics and physics processes, which are characterized by timescales which are comparable with a time step, and so need a few evaluation per time step. While finally, we have what we call super fast processes, which occur on shorter timescales, and so need many evaluation per time steps, and so they're usually treated with time step delta tau, which is shorter than delta t. And this is reflected in how dynamical core is structured. So this class receives not only the time step, the time step delta t and the current state, but also a bunch of slow tendencies. And then inside dynamical core, we have some concurrent couplet classes, which represent the fast and the super fast processes, which are invoked many times. And they are combined together with the slow tendencies in order to provide the state and the next time level. But on the other end, there are some coupling strategies which integrate the dynamics and the physics in isolation one from the other. These are the so-called splitting algorithms. And for this reason, we have the tendency stepper class, which is a wrapper around the tendency component and which uses the tendencies computed by the wrap class in order to move the solution, the state forward in time using some time integration scheme. So as part of Tasmania, we provide a few concrete time integrators, which mainly belong to the Runge-Kutta family. But of course, there are many other time integration schemes out there. In order to allow the user to add new time integration to meet their needs, we provide an extension mechanism which is based on the factory method design pattern. And now I'm quickly going to show how this can be implemented in Python using the classic example of the animal class. So animal is an abstract-based class which implements some public interface, here represented by the speak method. And then we have a registry, which is a dictionary which collects the derived classes, which implement the interface. And we have a factory method, which can access the registry and instantiate directly the derived class through some label that we have attached to the derived class. But how can we populate the registry? So if you assume that we have a derived class, dog, with just barks, then we can use the register decorator in order to inject this class inside the registry, attaching the dog label to this. And in this way, we make animal aware of the implementation, and we can let factory access and instantiate the child class. And this approach can be retrieved with as many derived classes as we want. So for example, with a cat and with a duck. And there's no need for all these classes to lie in the same module. Okay. And indeed, this is one of the advantages of this approach. So the fact that we don't need to modify already existing code in order to extend it, provided that we always instantiate the abstract method, the child class, through the factory method of the head class. And then registering a new method is as easy as using the register decorator. So we think this is a powerful tool, but we actually used quite extensively inside Tasmania, not only to implement the time stepper, but also for the topography, the horizontal boundary, in order to have different treatments of a lateral boundary condition, for some numerical dwarfs, which implement, for instance, horizontal diffusion and vertical wave absorption, but also for stencil-related utilities. Indeed, in the title, we claim that Tasmania is a stencil-oriented framework, and now I try to motivate this claim. So first of all, what is a stencil? So a stencil is an operator which computes a grid point value by accessing a fixed pattern of neighboring points. So for instance, in this illustration here, we have that the blue point is computing by accessing the 4 neighbor red points. And this kind of computational pattern is everywhere, not only in the dynamics, but also in the physics of our model. So this is kind of important. And then in the title, we have also another important concept, which is performance portability, which is about running a piece of logic optimally on a variety of architectures. And this can be achieved in 2 ways. So we can even manually write a different implementation of our code for different hardware or machine that we are targeting. This is a direct approach, gives us a full control over what we put inside the code. But at the same time, from a maintainability point of view, it's quite a nightmare if you end up with many machine or many architecture to support. On the other hand, we could exploit some automatic code generation techniques which can produce optimized code for and hardware-specific code for specific architectures, starting from a single application code which the user needs to maintain. And here, for demonstration purposes, we mix these two approaches by delegating implementation of a stencil operator to different backends. Two of these belong to, say, the manual branch. These are NumPy and CuPy, which are state-of-the-art tools in the Python ecosystem. And then we have GT4Py, which, as we will see in the next slide, is a domain-specific library for stencil applications. And then we also have limited support for Numba, which is a more general purpose just-in-time accelerator for Python code. And then Tasmania provides some backend specific utilities, for instance, to allocate memory in a way which is tailored to the different backend, register the definition function of the stencil, and finally combine the stencil into final code. So we provide some utilities to kind of automate and facilitate these routines. So here we give an overview on GT4Py, which has been jointly developed by CSCS and ETH Major Swiss, which is the Federal Meteorological Service in Switzerland, and the Vulcan company in the US. So the user-facing part of the library is a domain-specific language, which is called GTScript, which allow to express stencil computation in a descriptive and hardware-agnostic fashion. So here on the top right, we have a code snippet which implements, which better defines the Laplacian operator using GTScript. And then this definition function is translated into an AST-like intermediate representation called GTIR, which is then the starting point for optimization passes, which lower the GTIR into an implementation intermediate representation. And this is then consumed by different backends in order to produce code which is optimized for different architecture, which include both CPU and GPUs. The produced code is actually GridTools C++ code. So GridTools is another DSL, domain-specific library for stencil application, which is written in C++. And finally, the code which is generated is compiled under the hood and linked into the current Python code so that it can be accessed using a common interface. And this architecture allows to implement a separation of concerns between the domain scientists, which just needs to carry about the definition of the operation without caring about how to implement it optimally for a given architecture. This is something which is overseen by a performance expert, which is in charge of design and maintain basically everything from the front end down to the generated code. And then we can look at some performance figures. So, so far we have implemented two models on top of Tasmania, two idealized models. So one is the two-dimensional Vichy-Burgers equation. So a set of advection diffusion nonlinear equations. And then we have a mountain flow model in isentropic coordinates, which is fully three-dimensional and which is quite representative of full-fledged models, but still way more manageable. And we ran some simulations on the Pittsdent supercomputer, which is one of the largest supercomputer in Europe. So we ran simulation over a grid which consists of 161 points in the two horizontal direction and 60 vertical levels. We run for 100 time iteration in double precision. Although the level of precision can be set through some nameless files. And then we stress that we run on a single node of Pittsdent since multi-node simulations are not supported yet, at least not natively by the tool. So if we want to implement some scientific application in Python, typically we start off with NumPy, and we did the same here, and we got something like 300 seconds. And then we moved to GT4Py, and we were able to get a 15-fold speed up. And this is mainly due to enhanced data locality, some loop reordering, memory allocation, which is tailored to the backend, and some more optimization. Okay. And then we could lower the runtime even more by jumping to the GPU. And so first we may want to try out CuPy, basically because the API is the same as NumPy. It just needs to be fed with CuPy arrays instead of NumPy arrays, so that we can lower the runtime by another 50%. And then again, we can move to GT4Py, just changing the backend. And in this way, we get a threefold improvement, which finally gets to a 60 times improvement with respect to the original implementation in NumPy. And what should be noted is that only about half of the runtime of the GT4Py GPU implementation is actually spent in computing. The rest is overread due to bindings and counterflow. So we think that there is large room for improvement in these numbers. And finally, I would like to touch upon the couplers, which are the concrete, which take the components together in order to form a model. At the moment, we have 4 different couplers, which support 6 different physics dynamics coupling strategies. And here, as an example, we have the parallel splitting coupler, which, as the name said, implements the parallel splitting coupling strategy, which basically means processing the components in parallel and in isolation, and combining the provisional states through a data array dict operator, which basically delegates all the math operation to the proper backend. And here we remark that the components are actually interchangeable. So because they share the same interface, software compatibility is given for free, and the user, so the scientist, should just care about the physical compatibility between components, meaning, for instance, that we should make sure that a variable is produced before it is consumed by another component. And thanks to this flexibility, we were able to investigate the numerical properties of 6 different coupling methods. We gave her the results in a paper, which is now under review. And here we just give a glimpse over the results. So we focus on the convergence properties of the algorithm. So we perform an error convergence analysis by reducing the grid spacing and looking how the error decays. So here in these 2 plots, we have the grid spacing on the horizontal axis, decreasing from left to right, and the error with respect to a reference run on the vertical one. And we discovered that it is actually possible to achieve second-order accuracy using a 2 proper coupling strategy, here referred to as the full coupling on the left and the strength splitting on the right. So to conclude, I would like to mention that the full toolchain, so Tasmanian GT4Pi, is still under development, and so new features are like to be added in the future. All the code is hosted on GitHub, although Tasmania is still closed source, but it will be open up soon. And then we can say that it is true that we designed Tasmania and GT4Pi with weather and climate applications in mind, but I think it is suitable also for, and it can be applied to any other field, which basically apply separation between resolved processes and subgrid cell phenomena. And then, although the results are still quite preliminary, we can state that Python is a strong candidate for the next generation of model, but just as a user-facing and front-end language. Because due to the expressiveness of its syntax, we can much reduce the boilerplate as compared to Fortran. But on the other end, Python is too slow for computing, and so we should delegate low-level computation to some high-performance languages and paradigms. And finally, I would like to mention the Exclaim project, which within the next year will port the icon model to Python, so somehow following this research path. So with this, I conclude, and I thank you for your attention.